we learned empirical formulas, right? Was it stuck?
No.
We learned empirical formulas, right? We said there are empirical formulas and molecular formulas. Empirical formulas are just the ratio, okay? And the molecular formulas are the actual numbers in each molecule. That's how we do that.
Yeah, what number was that? 4, 2.
So we can go from our empirical formulas to our molecular formulas, but we have to be given the molar mass of the molecular formula, and we'll see that. Which C6H6 and C2H2, we said both had the same empirical formula, but they have different molecular formulas. Which one of these two has a greater mass? C6H6 or C2H2? C6H6, right? So the molecular weight of that is larger than that. We've done that. That was weeks ago, right? Because it's the same mass, the molar mass of this one is greater than that one. Okay? How much greater is the molar mass of that one compared to that one? It is 3 times larger. Okay? We're going to be looking at this ratio of molecular weights in order for us to figure out what the molecular formula is. To do the molecular problem, like I said, we have to have the molar mass. And it's going to be more or less the same exact problem as the empirical formula problem, but with one extra step on the end. Okay. Find the empirical formula. That is the first step. Yes, it's one step up here, but you know it's a whole bunch of steps, right? It's kind of like on the taco box. The first step is cook the meat, put the sauce in, put the water on, simmer it for 10 minutes. And the second step is make a taco and eat it. Right? So here the first step is find the empirical formula. The second one is divide the empirical formula's molar mass into the known experimental molar mass of the molecular compound. Okay? So experimental molar mass divided by empirical molar mass. And what you're going to get is you're going to get a ratio. You take that ratio and you multiply that by all the subscripts in your empirical formula to get your molecular formula. So if we had an empirical formula of CH, okay, and first of all, what is the empirical molar mass of, what is the molar mass of CH? Carbon is 12, hydrogen is 1, what's CH? 13. If I told you the experimental molar mass of our molecular compound is 26. If 26 divided by 13 equals what? 2. So you get 2. 2 is your ratio. Then you multiply the subscripts in your empirical formula, R1 and R1, by 2 to get C2H2. So that would be our molecular formula. Here is a bigger example. We have a compound. We know the empirical formula is CH2. Its molar mass is 42.12. What is the molecular formula? It's very similar to what we just did. So what if we have to do a division problem? What's on the top of our division problem? Yes. On the top is experimental molar mass. Our experimental molar mass is given to us as 42.12. On the bottom is our empirical molar mass. What is our empirical molar mass here? C plus H2 is about 14. We're going to call it 14. What is 42 divided by 14?
3.
Is it pretty close to 3?
3, yeah.
Okay. So we're going to call it 3. It's experimentally determined molar mass, so it's not exact. So if it's right just about 3, it's 3. So if our ratio is 3, and our empirical formula is CH2, what is our molecular formula? C3H6. We take our 3, multiply it by 1 to get 3, take our 3, multiply it by 2 to get 6. That's our molecular formula.
Now, because you did it this way, we don't have to simplify it then?
Right. It's asking for molecular formulas. It means you do not simplify. If you simplify, then it's empirical. What we're doing here is undoing the simplification, basically.
Okay.
But if you start with CH, you don't know if it's C2H2, C3H3, C4H4. You don't know. You can figure it out. If I tell you the molar mass, then you can figure it out which one you started at. Another one. Potassium persulfate. Percent composition of that much potassium, sulfur, and oxygen. And it's giving us the experimental molar mass. There's 2 steps to the problem. In this case, it's broken down into 2 different questions. While I'm on this, when you're doing homework or quizzes, make sure, or post-lab, if there are 2 questions in a problem, do them both. Okay? A lot of people read the first problem, do it, think they're done, and move on. Okay? That's particularly prevalent in post-labs, where it says, on the density one, what is the density of the cube? What happens if you cut it in half? That's 2 different parts. A lot of people didn't do the second part. Or, what if the question said, what happens if you do this, and why? Tell me what happens and why. Make sure you read the entire problem. So here, it's giving the experimental molar masses that. What are the empirical and molecular formulas? So the question is specifically asking you for both. So you have to give both. If the question was just asking you for molecular formula, you would still have to find the empirical formula to get the molecular. Okay? So what is my first step here? Convert to grams. How do I convert to grams? Multiply by 100. We're going to assume you have 100 grams. And so each of those percents become grams. So I have 28.93 grams of potassium. Grams potassium, and mole potassium. Potassium is 39.1. What does this equal? .739?
Yep.
0.739 moles of potassium. We have 23.72% grams of sulfur. Grams of sulfur, mole sulfur. Sulfur was 32.1, 2.1 equals 0.7389. 89 and 9. And then 47.35 grams of oxygen. A mole oxygen. Oxygen 16 equals
2.959.
2.959? 2.959 moles of oxygen. What's next?
Find the
Divide by
lowest.
the smallest.
Divide by the smallest one. So these are the same, they're both the smallest, right? So
1,
1, 1, what's that?
About 4.
Is it about 4?
1. Bless you.
So that's about 4. So what is my empirical formula?
KSO4.
KSO4. Everybody see that? Okay. So here's our empirical formula. That's the first part of the problem. Second part is what is the molecular formula? How do we go from this to a molecular formula?
Find out the mass of a mole of KSO4.
Right. So we find the molar mass of KSO4. And so somebody's going to have to tell me that unless it's up on the slide. Where is it up there? 135. 5.17. So the molar mass of KSO4 is 135.17. It says your experimental molar mass is 270.0. So what's our division? What division do we need to do here?
270 divided by 135.1.
Right. It's experimental divided by empirical, which is roughly what?
2.
Does everybody see that's roughly 2? There's 2. So what is our molecular formula? K2S2O8. Everybody follow from beginning to end. Do the empirical formula, find the molar mass of that, and now do your division. Experimental, which has to be given to you, divided by the mass of your empirical formula. It gives you your multiplication number, multiply all the subscripts in your empirical by that number to get molecular. We can also go the other way. Okay, we can go from our molecular or empirical formulas to our percents. When you do this, going the other direction, we assume we had 100 grams. In this case, we're going to assume we have 1 mole. So we can say, what is the percent sodium of Na2O? If we assume we have 1 mole of Na2O, how many moles of sodium atoms do we have? 2. We assume there's 1 mole of these, and there's 2 sodiums for every one of those. So we have 2 moles of sodium. How many moles of oxygen do we have? 1. We have 1 mole of oxygen. If we convert these to grams, we now have the grams of sodium, the grams of oxygen. If we add them together, we have the total grams. So we can figure out what percent is sodium, what percent is oxygen. So what is my unit here? Moles of sodium goes to grams of sodium. let's do 1 mole sodium. 1 mole of sodium weighs 23. And we have 1 mole of oxygen weighs 16. So this becomes 46. 6 grams of sodium, and this becomes 16 grams of oxygen. So if I wanted to figure out what percentage of my compound is sodium, what do I do? Right. So what is 46 plus 16? 62. So for sodium, I go 46 divided by 62. 62 came from 46 plus 16 equals 62 equals what? 74.2? 74.2%, which makes, so this one you can either do 16 divided by 62, or you can subtract that from 100. You're going to get to the same place. So what does this come out to be? 25.8%. This one was sodium, this one is oxygen. Got it? Here are 2 copper compounds. One is copper, 2 coppers and oxygen. Here is chalcocite, Cu2S. Which one has a higher percentage of copper?
Upright,
Why?
because oxygen has less mass than salt.
Right. So each molecule, or formula unit, or whatever you want to call it, has the same amount of copper in it, right? So the smaller the whole thing is, that means copper makes up a greater portion of it. Oxygen is lighter than sulfur, so Cu2O is lighter than Cu2S, which means copper makes up a larger portion of the cuprite than the chalcocite. Make sense? Okay. Now we can move on to chemical equations. Now we're done with the difficult math. Okay. There's still going to be a little bit of numbers here. But we're now moving on to our chemical reactions. Okay. We're done with compounds on themselves. Now we can start mixing them, making things happen. Okay? So, when you write a chemical equation, just like sig figs, this one's going to be more obvious to remember to do it. A chemical equation has to be balanced. And you'll see what I mean by balance. The number of atoms of each element has to be the same in the products as it is on the reactants. When we write the chemical equation, we take reactants. Reactants are the things that react. And we say the reactants yield products. So, however many of any given element you start with over here, they have to be here. Atoms do not get made. Atoms do not get destroyed. If it's here, it has to be here. Yes, it's going to get rearranged. It's going to be bound to different elements. But same number of each one has to be here and here. That's one way of looking at it. You can look at it in terms of elements being on the left and right. In a lab, when you're doing a reaction, we say you have conservation of mass. Whatever mass you start with, you have to have the same mass at the end. Mass doesn't get destroyed, mass doesn't get created. Okay? Mass, you start with a mass, You end with a mass. In some situations, a reaction may give off a gas. Gas has mass. It's just leaving. So if you have a sample and you say you have 10 grams of this A, 10 grams of B, you mix them together, it may give off a gas, and then you have 15 grams of AB. Okay? But that means 5 grams came off as a gas. The 5 grams didn't just disappear. So if you have a reaction and you're not losing a gas, your mass at the end has to equal the mass that you started with. This is a very powerful reaction. This is not like any reaction we're going to do in lab.
Oh, man.
So this is aluminum metal, and iron 3 oxide. If you heat it, you get a very, very, very hot reaction that forms liquid iron and aluminum oxide. So these are our reactants. These are our products. How many aluminums are on the left side? 1. How many aluminums are on the right side?
2.
2. Is that right? No. How many irons are on the left?
2.
How many irons are on the right? 1. Is that right? No. How many oxygens are on the left? How many on the right?
3.
So oxygens are balanced. We say the oxygens are balanced, but aluminum and iron are not balanced. So we are going to have to balance them. So just like we were saying, here's it drawn out. 1 aluminum on the left, 2 on the right. 2 irons on the left, 1 on the right. What do you think we can do to this equation to make it balanced? Right. So now we can move beyond our subscripts to what we call coefficients. So we have Al S plus Fe 2O3 Al2O3 plus Fe. The subscripts here are determined by the molecules themselves. The type of molecule we're using is F2O3. We can't change that. What we can do is we can say we have one of these aluminums, we have 2 of them, we have 3 of them, or however many we need. And we say that by putting a coefficient here. So here we have to have 2 aluminums. There's no choice. If we have a different number of aluminums, you have a different compound. So we can say we have to take 2 single aluminums over here so that they get combined together to be in our Al2O3. What about our iron? What can we do with our iron?
Put 2 in front of that.
Right. Here there's 2 irons, here there's only 1. You put a 2 there, now we have 2 irons and 2 irons. Everybody see how that balanced? Even though this iron has a 2 subscript, this iron has a 2 coefficient. What do you think would happen if I put a 2 there? Now how many irons do I have? 4. Right. So now we have 4 irons and 6 oxygens there. So watch out for that when you're balancing equations. There's a coefficient and a subscript for an element. You have to multiply them together to figure out how many of that element you have.
Does it work the opposite way too? Like if you did have 2 Fe subscript 2, would you put a subscript 2 over here?
No. Once you have the equation written, you cannot change the subscripts. You can't make them smaller, you can't make them larger. They are what they are. All you can change are the coefficients.
Okay.
So we can write our chemical equations with words or formulas. We're almost always going to do it with formulas. Okay? This is methane plus oxygen. That's methane plus oxygen yields carbon dioxide in water. Okay? Just like we said, subscripts are set. Cannot change them. They are what they are. And you count up how many of each element are on the left, how many are on the right. So here it's already done. Here there are 4 hydrogens on the left, 2 on the right, 2 oxygens on the left, 3 on the right. We need to balance this. Just like with Lewis symbols, this is going to be one of a brain teaser or a puzzle, not something that's overly complicated. Okay? So we have CH4 plus O2 yields CO2 plus H2O. The carbons are already balanced. So normally, just like with our Lewis, no, what was that? Yeah, with the Lewis structure, the hydrogen and oxygens always went on the outside, remember? If it was something other than hydrogen or oxygen, that was usually the middle. Here, you're better off starting balancing with the things that are not hydrogen and oxygen. So the carbon. But carbon in this case is already balanced. So I would go carbon and then oxygen. Is oxygen balanced? No. There are 2 here, 3 here. These over here, the oxygens always come in pairs, right? You have O2. If I put a 2 here, we have 4. If I put a 3, we have 6. They always come in pairs, which means I'm always going to have an even number of oxygens on this side, right? Here I have an odd number. So if I have an odd number of waters, I'm always going to have an odd number of oxygens over here, and it will never match over here. So the first thing I would do is make this an even number. I would put a 2 there. Now step back and see where you're at. Now I have 2 oxygens, 2 oxygens. I have 4 on the right. I have 2 on the left. Can I balance that? No. Yeah. If I put a 2 there, I have 4. I have 2 and 2 is 4. Now my oxygens are balanced. Carbon is still balanced. My hydrogens balanced.
Yes.
Yes. I have 4 and 2 times 2 is 4. So now that equation is balanced. Okay. Some of them, this is an easy one. You'll see some of them where you'll say you did this to balance the oxygens, and now your hydrogens are out of balance. So then you go and you balance your hydrogens, but then you throw your carbons out of balance. When you balance those, you throw the hydrogens back out of balance. That type of thing. And you just keep going and going and going until you get it to match. It's another one of those things, the more it's practice, the more you do it, the better you'll get at it. It's not that hard, you have to figure out the little tricks to get it done quicker. Here is some more to balance, and they're given to us in words. So potassium chlorate gives your yield potassium chloride and oxygen. What is the formula for potassium chlorate? ClO.
Is it over the only 4?
I think it's 3, but let's check.
It's 3.
Is it 3?
Yeah, that's your list.
Yes. Chlorate is 3 with a minus charge, so that is our potassium chlorate. potassium chloride is KCl plus oxygen. Is this, not worrying about balancing, is this written correct? No, what is wrong?
I see.
Yes, oxygen is diatomic, O2. Now we have to balance it. Are my potassiums balanced?
Yes.
Yes. Are my chlorines balanced? Yes. Are my oxygens balanced? No. But first thing that jumps out to me is, again, we have odd, and over there we always have pairs. So the first thing I would do is put a 2 here and now see. Are my potassiums balanced?
Nope.
What can I do?
Two.
Put a 2 there. Now my potassiums and my chlorides are balanced. Are my oxygens balanced? What can I do? I can add a 3. There's 6. 3 times 2. 2 times 3 is 6. Everything is balanced. There is hexane C6 H14 plus oxygen yields CO2 plus water. Start with your carbons. Are your carbons balanced? No. There's 6, there's 1. So let's put a 6 here. Let's go to our oxygens. Are they balanced? No. But again, we have pairs and odd numbers, right? So let's put 2. Let's put a 2 there. How many oxygens are on this side now? 14. 6 times 2 is 12, plus 2 is 14. There's 2 over here, but I can always do pairs. That one's easy. You can put a 7 there and you get 14. Are my hydrogens balanced? No. There's 14 and 4. So I'm going to have to change something. What do you think I should change?
Coefficient around 1.
Right. I'm going to have to change the coefficient in water. What I see is, on the right, if I can get my oxygens, no matter what they are, to be an even number, I can fix it with this one. So if I balance my hydrogens with an even number, then my oxygens can solve themselves. So I'm going to change this. What do I need to change it to? Be that. 7. Now that's going to be a problem, right? So what if I make this a 14, multiply it by 2, but now I need 2 of these. Okay? So now I have 12 carbons, 6 carbons. So I change this 6 to a 12. Now I have 12 carbons and 12 carbons. I have 28 hydrogens. I have 28 hydrogens. I have 24 plus 14 is 38 oxygens, right? So where's half of 38? 19. I will tell you, on a quiz, I would probably not give you one that difficult. But remember, I don't write the final exam. Yeah.
So is it better to leave things that stand alone, like oxygen, for last? It's kind of like a buffer for when you need to fill in spots.
The
like
things that are by themselves make your life really easy.
that. So save one for last to
Yeah.
get that.
Imagine how difficult this would be if instead of O2, this was SO2. So every time you change the oxygens, now you change the sulfurs too. But when you change the sulfurs over here, you change the hydrogens, and it just turns into a giant mess. Use pencil when you do this. Everyone see how to, it's just a matter of doing it, right?
Can you do another one?
Yeah. So zinc, this is just zinc by itself, reacts with hydrochloric acid, HCl, to give zinc chloride. Zinc chloride and hydrogen gas. Hydrogen is diatomic. It's H2. Okay. We really should be putting our state symbols. Sometimes I get lazy. Catch me. Okay. I don't think I didn't do that in the last two. So it's zinc metal. A metal is a solid. HCl, we're going to call it aqueous. Acid is dissolved in water. Okay, with aqueous, this is zinc chloride, which is aqueous plus H2 gas. I would start with my zinc. Is my zinc balanced? Yes. Is my chloride balanced?
No.
No. I can put a 2 here. Now my chlorines are balanced. Now my hydrogens are balanced. That one was easy.
It's a really dumb question, but how do we know if they're aqueous or not? Do we color that? Like, I feel like I'm drawing a blank. Like the zinc chloride says aqueous.
Yes, it is. If it's something, if it's an ionic compound and it's reacting, it's going to be aqueous.
Okay.
Ionic compounds as a solid don't really do anything. And that's later on in the, we're going to talk about all these reactions. Okay, here they are. 4 primary types of chemical reactions. We're just going to very briefly do generally what they are, not go into any detail, and then we'll take the quiz. Okay? So we have a starting point for Thursday. 4 types of chemical reactions. Decomposition, synthesis, or a combination, depending on who's labeling it. Just 2 different names for the same thing. Then there's single displacement. You may also see single replacement, and double displacement, or double replacement. Okay? At the bottom here, these are just atoms that we're going to use to demonstrate the different types of reactions. Decomposition is simple to recognize. You start with a complicated thing on the left, you get multiple less complicated things on the right. If there's only one reactant, the only thing it can do is fall apart. That's decomposition. Okay? Here's an example. If you have ammonium chloride, it can decompose into ammonia and HCl. There's one reactant that's more complicated than anything over here, so that decomposed into that. Synthesis, don't worry, we're going to come back to those, so I don't skip. Synthesis is the opposite. You have multiple simple things becoming one more complicated thing. Synthesis, you're making something, right? You're synthesizing something. You can take 2 elements to make one compound. You can take an element and add it to a compound to make a bigger compound, or you can take 2 compounds to make an even bigger compound. All that matters is that you're taking multiple things on the left and combining it on the right. Here's single displacement. Here we have an element and a compound. All that happened here is this A kicked out the C. So now instead of having A and CD, you have C and AD. Everybody see what happened there?
Mm-hmm.
And there's double displacement. In this case, you're starting with 2 compounds, and they just switch partners. That's all that happens. Okay? I can tell that we are going to finish these slides on Thursday. So I'm gonna put the homework up that has everything in it, but we haven't covered some of it yet. So just, we'll see, if we don't finish on Thursday, I'll take stuff out of the homework. Just don't go rush to do it tomorrow night and say we didn't cover this. Got it? Okay. Remember, we're gonna do the quiz. If you have questions about the homework, about last week's homework,